Okay, now this video here is about a special quantity that we often talk about in reaction kinetics, and that's something called half-life. And you might have dealt with this in your study of physics when you've done radioactive decay, the rate of radioactive decay, but we also use half-life in chemical kinetics as well. Okay, so what we'll do here is now we'll just remind ourselves from previous videos, what should the shape of these graphs be like? Okay, we want to review that first. And what we've got here is how is the rate affected by the initial concentration of substance for first order, second order, and zero order. So pause the video and think of what the shapes would be like, and then I can show you them. Okay? Okay. Well, here's the equation for a first order reaction. And this is another way to write it. We can write the rate constant there, and we have the concentration of A there to the power of 1. Okay? Second order, we have this, and here is the rate law. And zero order, we have this. And of course, rate is constant because anything to the power of 0 is 1. So the rate is constant, it doesn't change. And the shape of the graphs are like this. And you can see that the reaction rate is proportional to the initial concentration. So if you double the concentration, you double the rate, and we get the straight line. Here, if you double the concentration, you will quadruple the rate because it's raised to the power of 2. So we get this curved graph here. And for zero order, changing the concentration has no effect on the rate of reaction, so we get this straight line. Now these graphs are not to be confused with rate curves where you have time on the bottom here and you have concentration there changing with time. So we'll have a look at that later. Okay? So what we want to do now is we want to have a look at the definition of half-life. And the first thing to note here in this definition, it is the time taken for the amount of reactant to decrease to half the original amount. Okay? And it's given this symbol here, T half. So for example, if a solution has a concentration of 0.36 mole per dm cubed, the time taken to reach 0.18 moles per dm cubed is called the half-life because the concentration is halved, the amount is halved. Okay? Now we want to look at first order reactions, and really these are the only ones we have to deal with in the exam situation for half-life. And indeed, it's not even common in that either, but it's not difficult to understand, so we'll give this a try, okay? Now we know in first order, the rate of reaction is proportional to the concentration. As the amount of reactant decreases, then of course the rate decreases. Now, if it's proportional, when the amount of reactant is halved, then the rate should also be halved, shouldn't it, right? So if we take a look at this, let's suppose we start off with 200 grams, and in going to 100 grams, obviously that's called a half-life, and let's say it was 1 minute, okay? Now then, when the amount halves, the rate will halve, okay? Now what is the rate here in the first stage? The rate here is, it's changed from 200 to 100, so the rate is 100 grams per minute. But now the rate is going to halve because the concentration is halved. So the new rate here should be 50 grams per minute. So how long is this going to take? To go from 100 down to 50 at this rate, it's going to take the same amount of time, isn't it? 1 minute. Now, the rate is going to halve again to 25 grams per minute. And since the amount is halved, the rate will halve. So how long will it take to go from 50 to 25 at this rate? The answer is 1 minute. So what we've discovered is for a first order reaction, the half-life is constant regardless of the amount you start with. The half-life, the time taken for the amount to halve, is constant. There you go. This means that the reaction will have a constant half-life, the time taken for the amount of reactant to halve. And that's only true for first order, okay? And in fact, in this case, the half-life is 1 minute. Now, it's a pretty neat little thing here. The fraction of the original amount remaining is always 2 to the minus the number of half-lives. And this should be obvious because if one half-life has passed, then n is 1. And what is 2 to the minus 1? It is a half. So you've got half the amount left. Now, if 2 half-lives had passed, in the first half-life you'd go to half, in the second half-life you'd go to a quarter of what you started with. 2 to the minus 2 is a quarter. So you end up with a quarter of what you started with. So this is really neat when you've got a really awkward number to deal with. The number of half-lives is, of course, the time that you're looking at divided by the half-life. Okay? So the fraction of the original amount remaining is 2 to the minus the number of half-lives, which is the time you've got that's elapsed, divided by the half-life. Okay? Here's a little example here. 4 half-lives have passed here. So it's 2 to the minus 4, isn't it, right? So we're going to end up with, and we're going to start off with the first half-life, it'll be a half. The second half-life will be a quarter. Then we'll have an eighth, and then we'll have a 16th, won't we? Okay? That's what would happen if you had 4 half-lives. A half to a quarter to an eighth and to a 16th. And you end up with 6.25% of what you started with. In other words, a 16th of what you started with. Now here is a rate curve for a first order reaction, and you can see the time taken to go from there to there is this much, and to go from there to there is that much, and to go from there down to there is that much. The half-life is constant. First half-life, second half-life, third half-life, it's constant. And here's the only reaction that it applies to. It's got to be first order for a constant half-life. Okay? So as an example here, if you start off with this concentration, when the concentration halves, the rate will halve. So that means this gradient should be half as steep as that gradient there, isn't it? Okay? Now, here's an example of a first order reaction. The rate of this reaction is first order with respect to bromine. Okay? It's actually first order with respect to methanoic acid as well. But because bromine is brown and these products are colorless, you can actually look at the absorbance with time, okay? It starts off a yellow-brown color, which is bromine, and it ends up like this, it's colorless, okay? So you can follow absorbance with time. Now, let's have just a quick look at second order, okay? Although I don't recall ever seeing a question on this, but it's not difficult to understand. You know that the rate is proportional to the square of the concentration. So if the concentration halves, then the concentration is halved, so the rate will go down to a quarter of what it was. Okay, here we go. When the concentration is halved, the rate of reaction will go to a quarter of what it was. So using the same kind of scheme again, let's suppose this took 1 minute to go from there to there. Now the new rate there, this rate here, by the way, is going to be 100 grams per minute, but now the new rate, because the concentration is halved, the new rate is going to be a quarter of what it was. So the new rate will be 25 grams per minute. That means this would take 2 minutes to happen, because you're going from 100 to a 50 at this rate. It would take 2 minutes. Look, the half-life has doubled. Now, what would happen if we go from there to there? The rate would go down to a quarter of what it was again. So the rate would become 6.25 grams per minute. How long would this take? That change there is 25 gram change, and it would take 4 minutes. Look, the half-life has doubled again. So for second order, the half-life is doubling each time. Okay, and it looks, don't get tricked here, it looks a little bit similar to a first order curve, but the half-life is increasing. The second half-life is twice as long as the first, and the third half-life is twice as long as the second. Okay, and you can study the graph to make sure of that. And this is true for second order reactions. For example, these two are both second order. Okay, and here we go. When the concentration is halved, the rate will go down to 1/4 of what it was. So the rate for this one here is going to be 1/4 of the rate that it is there. Okay, there we are. This rate here is a quarter of the first rate there. Okay, there we are. There's the same thing there. Okay, and now we have a look at zero order finally. And for zero order, the amount of reactant has no effect on the rate of reaction at all. So if the concentration was halved, there'd be no effect on the rate. Now the first half-life here is 1 minute, we'll say, and the rate must be 100 grams per minute. When the amount halves, the rate will not change, so the rate remains constant. So how long will this take at this rate? It would take a half a minute, so the half-life is halving. Now the concentration is halved again, there'll be no effect on the rate would be the same. How long will it take to lose 25 grams at this rate? And the answer is 1/4 of a minute. So the half-life keeps halving. Okay, the rate of the reaction rate is not changing, and it's got a decreasing half-life, and it's halving each time. Here we go. A straight line, constant rate, constant gradient. Here's the first half-life. The second half-life is half of that one. The third half-life is half of that one. Okay? Again, I've never seen a question on the half-life for zero order, but it's kind of useful to know. And it's for this type of rate law here, isn't it?